To understand polar equations by symmetries, we want to understand that there are three main types of symmetry that polar equations may have. This will allow us to graph polar equations more quickly by only having to graph part of it and then repeat it for the rest. So, reflection over the horizontal axis, so that would be something along the lines of, if you saw that would be a reflection across the horizontal axis. This would be a reflection across the vertical axis. And a rotation about the pole would be something along the lines of that. And to be fair, this has all three of them because it's reflective left-right, it's vertical up-down. An example where it does not have reflective symmetry across either of those would be something like that. Examining the symmetry of a polar equation can save time when graphing by evaluation. So if you know that it has horizontal symmetry, left-right, then what you can say is, well, once I graph these points, I know that I can also graph those points as well. So to reflect over the horizontal axis, what we have is, here's r comma theta. The idea is that this is being reflected down here. So r is going to stay the same, but instead of going positive theta, now we're going in a negative direction. So this is r comma negative theta. To reflect over the vertical axis, we have this is being reflected over this way. Here's theta, and this describes here. So this angle is also going to be negative theta. We know that over here the angle is pi. So then this location is r comma pi is the angle here minus theta. So we can replace theta with pi minus theta, and that would reflect over the vertical axis. To reflect about the pole, well, that's saying that we're going to take this theta here, and we're going to continue on the other side. So that would be theta, and then over here was pi. So then this would be r comma pi plus theta. So far we have negative theta, pi minus theta, and pi plus theta as our three different ways that we can have symmetry. So to test for symmetry, you can replace r comma theta with these things in order to determine which type of symmetry it has. So what that means is, if you replace r comma theta with r comma negative theta and you get back the same equation, then it has reflective symmetry across theta equals 0. If you replace it with pi minus theta, then it has reflection across this. And if you replace it with this and you get back the same original equation, it gives you a 180-degree rotation. So let's identify which symmetry this has. Well, let's start by plugging in negative theta. If we do 1 minus sine of negative theta, that becomes 1 plus sine of theta, because sine is an odd function, so this is not the same, therefore it does not have the first symmetry across theta equals 0. Theta equals 0 is false, or it does not reflect across theta equals 0. The second one, if we replace it with pi minus theta. So if we replace sine of theta with sine of pi minus theta, I believe that does give back sine, yes. So for 1 minus sine of theta, therefore this does have reflection across pi over 2. If you want to check the last one, it doesn't have the last one, but just to show it, for 1 minus sine of pi plus theta, that is not symmetrical, so it does not have rotational symmetry. What type of symmetry does this have? Well, when we replace this with negative theta, cosine of 3 times negative theta, I believe 3 times negative theta is negative 3 theta. And when you take the cosine of a negative angle, it gives you back the same thing. So this does have reflective symmetry across theta equals 0. So in other words, this one, once we find whatever it looks like on the top, I don't remember what it looks like on the top, then it'll give you the same thing. What type of symmetry does this have? Well, if we replace with negative theta, we get negative 2 theta, which we saw earlier does not work. If we replace it with pi minus theta, we get 9 sine of 2 pi minus 2 theta, which is 9 sine of negative 2 theta. Yeah, that doesn't work. That's not the same. If we replace it with sine of theta plus pi times 2, what we get is 9 sine of 2 theta plus 2 pi. But because this is one period, we know that that doesn't change anything. So this is 9 sine of 2 theta, and that is the same. So in other words, this has rotational symmetry by 180 degrees. Thanks.